In this video, we are going to do some more examples using the derivative rules. So we have these two functions, r of x and t of x, which are these two polynomials. And the question is, we want to find, or at least the problem is, find all x values where the tangent line to r at x comma r of x is parallel to the tangent line to t at x comma t of x. So if I want my tangent lines to be parallel, that means they should have the same slope. So we need the slope of the tangent line to r to be equal to the slope of the tangent line to t. And the thing that tells me the slope of the tangent line is the derivative. So tangent line to r, that slope is going to be r prime of x. And for the tangent line to t, that slope is going to be t prime of x. So we need to take these derivatives and then set them equal to each other. So this is where we can use all of our derivative rules now. The derivative of r, when I bring that 3 down, it's going to cancel the 1/3. And I'll get x squared, because I subtract 1 from the power. Doing that with a 1/2, the 2 comes down, and it cancels the 1/2. And I'll get just x to the 1, the derivative of minus 6, is going to be, technically this is an x to the 1. The 1's going to come down, it's going to multiply the 6, and I'll get negative 6. And then we'll get x to the, subtract 1 from the exponent, and I'll get 0. And the 5's a constant, so its derivative is 0. So I don't need to write that. So that's the derivative of r prime of x. If you're not totally sure how I got this, I'd encourage you to watch the previous video or rewatch it, because that's where we talked about how to do derivatives like this. And then for the derivative of t of x, when I bring this 4 down, it cancels that 1/4. And I'll get x to the 3, because I subtract 1 from the power. And then 1/3 x cubed, well, we already did that one in r of x. That's going to be plus x squared. With a minus 3 have x squared. We bring the 2 down. And that'll cancel the 2 on the denominator. So I'll have minus 3. X to the, subtract 1 from the power, and I get 1. Derivative of minus 6x, we already did. That was minus 6x to the 0. And x to the 0, that's just going to be 1. So x to the 0 here, that's just going to be 1. Okay, so in practice, we won't really write the x to the 0. We'll just write minus 6. That ends up being simpler. Here as well, we'll write minus 6. All right, so we have these two functions, and I want to figure out when this equation is satisfied. So I noticed that we can cancel an x squared from both sides and cancel a negative 6 from both sides. So I want to talk about two ways of solving this. The first, which is incorrect, because this is a common method that I see people doing, and I want to talk about why this is not right. And then after that, the correct method. So it's important to discuss both of these so that we can recognize what makes the incorrect method incorrect and help avoid falling into that trap. Okay, so what is the incorrect method? Well, so on the right-hand side, I have this x cubed term and this minus 3x. Maybe that we can move the minus 3x over to the left, and that gives me 4x. And then we have x cubed on the right. And now both sides have an x, so I can divide by x. So we get 4x equals x cubed, and let's divide both sides by x. And on the left, I get 4. On the right, we get x squared. And then square rooting both sides, we get that x equals plus or minus 2. So we get x equals plus or minus 2. So there's another value of x that actually works in this original equation. So, but pause the video for 30 seconds and see if you can identify what is that other value of x that satisfies that original equation. 4, 3, 2, 1, pause the video. Pause the video for 30 seconds and see if you can figure out what that missing solution is. All right, so hopefully you've done that. Hopefully you've paused the video to think about that. So the thing is that x equals 0 also works. X equals 0 also works. Which leads us to ask, why did we lose an answer doing it this way? And this, now I want you to pause the video one more time, this time for 1 to 2 minutes, because this is the question that's at the heart of this and why this method is incorrect. 4, 3, 2, 1, pause the video. Pause it this time for 1 to 2 minutes to think about what was wrong about this. Where did we make a mistake? All right, so hopefully you've done that. Hopefully you paused it for about 2 minutes to really think about what went wrong here. Where did we break a rule? And it turns out the step where we broke a rule is this one, where we divided both sides by x. Because this is not something we can do for every single value of x. There's a problem if x equals 0, because then my denominator is 0, and that makes my fractions undefined. And notice 0, that's the answer that we lost. We didn't end up getting 0 as an answer. And that makes sense based off of the fact that when we divided both sides by x, that only works as long as x is not 0. So there's a problem, whoops, I should connect that with this. There's a problem if x equals 0 in that step. So the moral here, so the key takeaway, now that we've identified that error, the moral is we actually never want to divide both sides of an equation by a variable. Because if we do, like we divided both sides by x here, we might be dividing by 0, and that's a problem. So never divide both sides of an equation by a variable. Doing so may cause us to lose solutions. Okay, so you might have remembered from maybe algebra that whatever you do to one side of an equation, as long as you do it to both sides, we're good. There are certain exceptions to that. And one of the exceptions is dividing both sides by a variable. That's actually not something you're allowed to do to both sides of an equation because of this problem of dividing by 0. Okay, so instead, anytime we are tempted to do that, this is what we should do. Instead, what is the correct method? Instead, what we should do is move everything to one side and factor. So move everything to one side and factor. All right, so if we did that instead, if we had taken this 4x and just moved it to the right-hand side, we would have gotten 0 equals x cubed minus 4x. And now I could factor that x out. So we had x times x squared minus 4. And I could factor this further now, actually. This is x, and then this is a difference of squares. I got x, oh, sorry, not x squared. This would be x minus 2, and then times x plus 2. And now it's factored as much as I can. Now let's set everything equal to 0. So either the x equals 0, or x minus 2 equals 0, and that makes x become 2. Or from the x plus 2 being equal to 0, that gives us x equals negative 2. Okay, so this way we are getting all 3 solutions because we didn't break this rule of dividing by x and possibly dividing by 0. Okay, so moral again, never divide both sides of an equation by a variable because you might lose a solution. Anytime you are tempted to do that, instead, move everything to one side and factor. So let's do one more example to wrap up this video. Okay, so let's let g of z be 3 times z cubed minus 5, that quantity being squared. Differentiate g of z. So differentiate is just a word that means take the derivative of. So we're taking the derivative of g of z. So, I see this 2 as a power, and it might be tempting to say, wait, 2, bring that down, and then subtract 1 from that 2. So we're sort of thinking of the power rule. But the power rule works when we have like 3 times z squared, but not when the z itself is this complicated looking function, but not for 3 times some stuff squared. So the power rule can handle this, but not the 3 times stuff squared. We'll deal with stuff like this, 3 times stuff squared, with a rule called the chain rule in section 4.4. And that's a rule that'll let us handle compositions of functions. So when we have functions being plugged into other functions and how to take the derivative of those using a rule. But we can actually do this using our current knowledge. So using our current methods, we first have to simplify this to a form. We first have to put this into a form that we can actually handle using our current rules. So we're going to first expand this. And so I have this thing squared. Let's just square that out. So g of z, which is 3 times z cubed minus 5 squared, which means z cubed minus 5 times itself. And let's expand. So we have g of z equals 3 times, and foiling this out, we'll get z to the 6th minus 10z cubed plus 25 once we FOIL. And now if we distribute the 3, we get 3z to the 6th minus 30z cubed plus 75. All right, so that is g of z. Now it's finally in a form we can take the derivative of. All right, so this implies that g prime of z, the derivative, using the power rule, the 6 comes down, and I'll get 18. Z to the 5, because I subtract a 1 from the power. Notice I'm upping the speed a little bit. The more and more of these derivative rule problems I do, the more I'll sort of up the speed until we get totally comfortable with it. So then the 3 comes down, and I'll get minus 90 z squared, because I subtract 1 from the power. And then 75 is a constant, so that derivative is 0. And that is my derivative right there. All right. So the moral for this example is, when we do a derivative, we really need to be sure that when we think about a rule, in this case it was the power rule, that the function that we have can be handled with that rule. And initially, the power rule could not handle this. It was something that we just can't handle with the power rule. Power rule doesn't work for stuff of this form, so we had to rewrite it. In this case, we had to expand it. And once we did, we could then handle it with the power rule, and also we used the sum and the difference rules and constant multiple rule. So that was kind of the moral there. Put it into a form that we can handle, and then use the rules that we already know. But later in section 4.4, we will learn a better way for doing this, using the chain rule. All right, so we've made it to our last goal of this section, which was just doing more derivative examples.